Hello, we are Team 8 and our project is called Rookma No Hands. So a brief update on the project description or a recap of the project description. We are designing a self-moving chessboard, which the idea is to basically be able to play against another player that is somewhere not in the room or against an AI. And basically you can make your moves physically while the other player will basically be able to make their moves over the air. So this supports virtual opponents and local control on the board playstyle. The motion is facilitated by a electromagnet under the board, which will move the pieces that have magnets in them. Our idea is to create a chessboard with a very robust design in order to be able to have a rigid chessboard that people can play on and use multiple times.
The biggest progress we've made in terms of the sensing subsystem this week would be programming the 3x3 prototype, which you can see in the image on the bottom right below. This works basically exactly as we intend. It will read the values that are on each of the sensors and broadcast those over serial, just in the form of a grid of true, false, basically. We've also designed the PCBs, which will house the actual sensors used in the chessboard, but we did encounter a setback as we realized we needed to implement diodes in order to protect the outputs on each of the sensors, because without those in place, the sensors were interfering with the other ones that they were connected to.
Okay, so I'm going to be going over the design progress from the software perspective, which we made since the last presentation. So first moving on to the motion control. So we have successfully generated G-code commands for moving the gantry. So we have generated G-code commands for moving the gantry to all in each specific square of the chessboard. So basically from A1 to H8. So for example, if you see a sample G-code here, so we have M62, which N62P0 is a command that turns the magnet on. And G0 and G1 are basically commands which are used to move and CNC machine using G-code. So G0 is basically travels rapid movement to the center of the square of A1, the A1 chess square of the chessboard. And then we have G1 X45Y15 F100, which moves the gantry to the center of the square B1. And F100 is basically the feed rate. So at a feed rate of 100 rates per second, and once it moves over there and we turn the magnet off with the command M63P0. So basically we have commands like this for all the possible moves and combinations and positions of the chessboard. Now moving on to the connectivity, we have an AWS server setup. So the ESP32 board is connected to the chessboard and initialized. So the initial state of the chessboard is up and running on the server. So the chessboard data is transmitted to the server, and the server keeps updating the server-side representation of the chessboard continuously. So the process is repeated, and we can also request the state of the chessboard from the server. And meanwhile, the updates will be passed. So we have an AWS server up and running. And what we're currently working on is the sensing coprocessor functionality. So we basically want a coprocessor to check the state of each sensor on the board and communicate to the main board. So we will check for changes in state of each sensor. So if a move has been made or a piece has been captured and so and so. And so basically this will just send a bunch of commands like a move has been made or some change has been sent, like a small set of command like that to the main board. And the main board will acknowledge that. And likewise, the main board can request the current state of the board from the coprocessor. This is what we're currently working.
So our main design progress for this week comes from the game logic design. And we sort of had a discussion about how we were going to approach writing the firmware for our game logic. So the first choice was that we would have our opponent always be an AI versus having to create a sort of virtual opponent that would simulate someone on the other side of the world playing the board. The idea is that essentially, because the AI opponent and commands are given the same way that we would give a real life virtual opponent on for someone who's not playing in the room. We have also decided on what kind of system we would choose for each of the moves and how we would determine how the state goes from one state to another. Due to the Hall effect sensor choice, the player will be required to move the capture piece off the board first before placing the new chess piece on the square. This is to facilitate the ease of knowing which piece has been taken when a piece is eventually captured. In the case that two possible pieces or two or more possible pieces can be captured, we need to figure out which one is captured, and the only way to do that is to sort of do it systematically by checking the whole sensors through a cycle and determining if a piece has been moved off that square. We also have determined that we will use the Lichess API for a chess engine, which will be used to storm the game data offline or off to the side. And this API will also be able to determine whether any illegal moves have been made or if a state of the game has ended, basically due to checkmate, stalemate, or draw. Finally, we decided that the former language will be switched to Python for the ease of implementation, as again, C is very difficult to implement some of the arrays and dictionaries that we would want to normally implement in a Python language. So additionally, the Lichess API is written in Python, so communicating with the server will be much easier if the languages are the same. And additionally, creating the chess algebraic notations is much easier to do with strings in Python than with strings in C, which you will have to pre-allocate.
Just to give a little update on the design progress for our, I guess, the manufacturing progress, not really design progress. Half the parts have been completed, which is great. The fit is going pretty well. Here and there's some issues with making sure that press fits are working, but you can see we've received our ground Thompson shaft ways, and they're beautiful, perfect, and they're fit into the end blocks here, here, and here. So that fit's going well. Next is to do the translational movement aspect. All the bearings have been fabricated. They're all finished. They're all within 0.5 of tolerance. And then I also manufactured these motor mounts. So everything should remain flush across the surface so the motor shafts can ride, the motor belt can ride flat across the surface of the gantry. Only thing that's remaining is to keep making progress on parts, which is going well, if a little bit slowly. So I hope to be done by early next week.
Okay, so I'm going to talk about the interview we had with the computer engineering grad student from Northwestern. So they wanted to know if instead of using Hall effect sensors, we could have used maybe like a piezoelectric or an IR sensor to detect when like pressure is taken off, like when the piece is lifted, when the pressure is detected, it can piezoelectric can send the sensors can send some sort of voltage and detect some sort of voltage change, and maybe we could have gone for such an approach. And they're also concerned about the power issues because we're using so many components. So they were concerned about the power issues. And because of the gantry and all the bearings and all the motors we're using, they wanted to know if the chessboard will be heavy. They were just concerned that the chessboard might be like very heavy. And also they wanted to know in case one of our processors fails, what our contingency plan would be. Because in case one of the sub-processors fails or the main board fails, they were a little curious as to what are, maybe we should have some, they were suggesting that we should have some sort of contingency plan. On the other hand, the feedback was pretty positive. They felt that the design was very innovative and aesthetically pleasing. And they also mentioned that coding up an entire firmware for a chess game would considerably hard, considering the game logic, the capture logic, and how to detect if a piece is moved. Considering everything, it would be considerably hard. So they suggested using a chess engine or a chess API.
One of the new things we learned about this week was the need for diode protection. So as mentioned previously, we encountered a problem with our Hall effect sensors in which the data was basically getting interfered with. As we figured out the problem was that our sensors are active low, which means that they're going to be outputting a high voltage in the case where there's no magnet in their presence. As it turns out, if you apply a high voltage from elsewhere to the output of one of the sensors, that will be enough to power the whole thing. So what was happening was that every sensor in our grid was being powered directly. Therefore, whenever you had a magnet in the presence of any sensor, it would pull the whole column of sensors to ground, which made the whole idea of trying to figure out which square specifically has a magnet on it, it made that effectively worthless. So we did implement another prototype, another version of our prototype, or a modification to it, I guess, which contains diodes on the outputs, and it works exactly as expected, which is very good here. But yeah, this is definitely something that we are going to need to keep in mind in any future circuits that we're going to be designing.
For our first question, we have decided to change our firmware programming language to Python because we believe that it's easier to program some of our code in it, especially the game logic, which requires the use of multiple collection of board states. And essentially, because we don't know the certain amount of board states that we will have to collect over a certain period of time, it's easier to facilitate the memory in Python than it is to do in C. So our question to you is whether you think we made the right decision in switching from Python to C on the ESP32. And if you sort of have an experience in doing so, what are some of the recommendations that you have in programming in Python on the ESP32?
All right, so for our second question, we want to ask a bit about how you guys think it would be best to implement the logic for move interpretation. So as we mentioned previously, we're moving into the software phase, so this is becoming more and more of a pressing issue for us. So our current plan would be to basically constantly pull the sensors on the grid. We would note anytime there's a change in value, and that would basically add a description of what that change of value is to a list. So basically, over the course of a move, you will get your whole set of shifts in pieces, or like at least changes in sensors, like where pieces were picked up and put down. And then based on that, you can do logic on it in order to determine what kind of move it was. Like, did you just pick up a piece and set it down? Did you pick up a piece, pick up another piece, and then capture that piece? That kind of stuff. All right, but yeah, so if you have any advice on what you think we should do, that's a fresh idea from you, or if you have any suggestions to improve our current plan, we'd appreciate hearing about that.
Thank you for listening to our presentation, and we appreciate the feedback that you will give us.